Good morning, everyone. My name is Pairayaphak Ngamplang. I am studying in the third years of the doctoral degree in polymer science program at the Petroleum and Petrochemical College, Chulalongkorn University. It is my pleasure to present our research topic is development of terpinen-4-ol beta-cyclodextrin liquid bandage with controlled release and antibacterial activity. Let me begin with the background of this study. Wound management remains a significant challenge in healthcare, especially due to the risk of bacterial infections. Open wounds provide an ideal environment for microbial growth, which can delay healing and increase complications. This slide is the traditional wound dressings such as the gauze. They may not provide suitable antimicrobial effects. And in recent years, liquid bandages have gained attention as the alternative. They are easy to apply, form a thin, productive films, and can conform well to irregular wound surface. Now, one promising antibacterial agent is this terpinen-4-ol. It is the main active compound of the treaty oil. It is well known for its strong antimicrobial activity. However, there has remained drawback. First, it is highly volatile. Second, it is poor water solubility. And the last one, it has low stability when exposed to the environmental conditions. So the key questions we asked was how can we improve their stability and control the release of terpenen-4-ols in the wound dressing system. So the objective of this study is to develop a liquid bandage system that can provide controlled release of terpenen-4-ol while maintaining strong antibacterial activity. Specifically, we aim to improve the stability of the active compound, achieve sustained release over time, evaluate antibacterial performance, and understand that the molecular interactions within the system. And in recent years, researchers have been trying to find a way to protect and preserve essential oil and their active compounds. As shown in this screen, they can be encapsulated in various delivery systems, such as polymer-based nanocarrier, lipid-based nanocarrier, and molecular complex. In this work, I'm focused on molecular complex because this method can enhance bioavailability and stabilize the physical and chemical property of essential oil and their active compound. For the molecular complex method, it consists of two parts. The first part is the host molecules, such as β-cyclodextrin, which has the tourniquet Chulalongkorn and is produced from the stud degradations. Beta-cyclodextrin has the secondary hydroxyl group at the larger cone border, and it has the primary hydroxyl group at the narrow cone border, giving it has the hydrophilic outer surface. And the skeleton is the carbon, result in the hydrophobic cavity. And the second part is the gas molecules, which is the hydrophobic, such as terpenen-4-ol or essential oils. When the gas molecules have their interactions with the host molecule via non-covalent interactions, the inclusion complex is formed. So this inclusion complex can be enhanced solubility and bioavailability, improve stability, provide controlled release, and reduce toxicity and irritations. Moreover, it can decrease the volatility. Now, let's move on the material used. The active compound in this study is terpinen-4-ol, and to enhance its stability, we use beta-cyclodextrin, which is cyclic oligosaccharide, known for its ability to form the inclusion complex. And for the polymer matrix, we select PVA and PAA. These polymers were chosen because they are commonly used in biomedical applications and can form stable films suitable for wound dressing. And next, I will briefly describe the methodology. First, we prepare the inclusion complex by using coprecipitation method. And this allows terpinen-4-ol to be encapsulated within BCD cavity. After that, we fabricate the liquid bandage films using polymer matrix. We then perform the similar technique for characterize the occur of the inclusion complex and the property of the liquid bandage, including drug release study under different environmental conditions, antibacterial testing against common pathogens, cell cytotoxicity, and the molecular dynamic stimulations to understand the interactions at the molecular level. After that, molecular dynamic stimulations were conducted, beginning with the molecular docking, to obtain information such as the conformations of active compound inside beta-cyclodextrin cavity. And the first step involved drawing the chemical structure of the active compound using gauge wheel, and then the docking evaluations were then performed using Discover Studio 2017. Subsequently, the MD simulations were carried out using Ember 22 package, and the results were analyzed. Let's take a closer look at the inclusion complex. NMR spectroscopy were employed to confirm the formations of the inclusion complex. As I explained in the previous slide, we know already, beta-cyclodextrin is the tourniquet hollow cone border, and it has the two distinct regions. The first one is the external hydrophobic surface. It consists of H1, H2, and H4. And in the internal hydrophobic cavity, it's composed of H3 and H5 proton. The non-covalent interactions between terpinen-4-ol and the hydrophobic cavity of beta-cyclodextrin, resulting in change of the chemical shape of H3 and H5 of the inclusion complex, which serve as the key indicator that the inclusion complex is forming. Moreover, the NMR integrations of the inclusion complex indicate that the inclusion complex exhibit a one-by-one host gas interactions, meaning that one molecule of terpenen-4-ol is encapsulated by one molecule of beta-cyclodextrin. Therefore, our result confirmed that terpenen-4-ol was successfully encapsulated inside the beta-cyclodextrin structure. These encapsulations provide several advantages. It reduces volatility, improves chemical stability, and enable controlled release of the active compound. And this step is crucial because it directly addresses the limitations of terpenen-4-ol. Now I will describe the drug release behavior. We conduct release study under the various conditions, including pH level of 6.8 and 7.4, temperature 37 and 70 degrees Celsius, and different humidity level. The results show that the system was able to sustain the release of the terpenen-4-ol up to 3 days. Importantly, pH play a key role in the release behavior due to the presence of PAA, which exhibits the pH responsive property. As the pH increases, the release rate of the inclusion complex also increased. This is because under alkali conditions, the carboxy group of PAA become deprotonated and convert to negatively charged of COO-. This charge creates electrostatic repulsive within the polymer chain, leading to expansions or swelling of the PAA network. As a result, the structure becomes more open, allowing a faster release of the inclusion from the liquid bandage. In contrast, at the lower pH, the polymer chain are less ionized and less solvent, resulting in a slower release. Moreover, we also observe that the higher temperature increases the release rate, while the higher humidity further accelerates the release process. This finding indicates that environmental conditions play an important role in controlling the release behavior of the system. Next, we evaluate the antibacterial activity. We test the system against two common bacteria, S. aureus, which is gram-positive, and E. coli, which is gram-negative. This result demonstrates that the liquid bandage exhibits significant antibacterial activity against both strains. This confirms that terpinen-4-ol retains its biological functions after encapsulations. Importantly, the controlled release system helps maintain antibacterial activity over a longer period. In addition, cytotoxicity studies show that the formation is non-toxic to cell, indicating good biocompatibility. Furthermore, this system also promotes the tissue regeneration, showing improved healing potential compared to the commercial product. Overall, this result highlighting the advantage of our formulations, not only in preventing the infections, but also actively supporting the wound healing process. To gain deeper insights into the system, we conduct molecular dynamic simulations. The results show that the system is stable after 500 nanoseconds. And here is the clip video that represents the interactions between inclusion complex with PVA represented in the red color and the PAA represented in the blue color. Looking more closely at their interactions, the inclusion complex were able to interact with both PAA and PVA matrix. However, it showed the stronger binding affinity with the PVA as shown in the correct video and shown in this heat map. See, for the inclusion complex with PVA, it will be shown the darker blue color than the PAA with the inclusion complex. So, the weaker interactions of the PAA matrix is particularly important for the release behavior. Specifically, at the lower pH, the polymer network becomes less solvent, resulting in slower release. On the other hand, at the higher pH, the PAA chain tends to swell, which facilitate a higher release of inclusion complex. The trend is consistent with the dark release result presented in the previous slides. And based on this finding, we propose the following mechanism. Β-cyclodextrin acts as a carrier that encapsulates the terpinen-4-ol, while the polymer matrix regulates the diffusion of the compound. Together, They create a system that enables sustained release, reduce volatility, and enhance antibacterial performance. To summarize the key findings, we successfully developed a liquid bandage with controlled release property. The system shows strong antibacterial activity and good structural stability. In terms of applications, this system has potential in the wound dressing, medical, coating, and drug delivery system. However, these are still limited. However, there are still limitations because of this study is not just being tested in vivo. So for the further study, we plan to conduct in vivo experiments, optimize the formulations, and explore large-scale productions. Finally, I would like to acknowledge our research team, Chulalongkorn University, and all funding research. Thank you very much for your attention, and I would be happy to answer any questions.